All right. So good morning. And so today we'll continue talking about the empirical Bayes method, and we'll basically do a few case studies that'll demonstrate how we can use real data for the purposes of an EB evaluation, and we'll compare that to a before and before and after with control. Now, before we get too far into that, so like I said, the main focus, I've introduced these concepts to varying degrees. Now, we didn't meet in person last week, so I wanted to make sure we went through this live at least once. And so I was trying to figure out when to have due dates. I didn't realize I initially had the exam scheduled for this week, which isn't happening for various reasons. And so I didn't want to necessarily have you guys take both exams next week. And so tentatively, I was going to suggest we push it back to, say, the 26th. Does that seem reasonable on your end? Okay. Because I'm assuming these are the only two classes you guys are taking now. Is that right? Are you taking anything else? Okay. Okay. And so I'll have a homework assignment that should go out today it'll be similar to the content we've covered today. And then I'll have some additional slides where we'll actually estimate some safety performance functions. And I'll try to get those up still this week as well, but I want to make sure you guys have at least a week to work through that. It looks like Dr. Gates used the same cable barrier data set that I had used previously, so I'm going to try to find an alternate. Although I think, if I recall, Jordan, you're the only one that had worked with that data in any degree, right? So, um, anyway, so that's what we're looking at in terms of the schedule here in the near term. Um, and so, like I said, now the main thing I wanted to do is just kind of work through each of these methods using some real data. And I'll introduce a sufficient amount of the background probability and statistics here, but probably not delve too much into derivation or anything of that nature. So it'll be somewhat conceptual and then somewhat aimed at familiarizing you with the various terminologies. And so a lot of this is following some content developed by Dom Lord, who's a researcher at or faculty at Texas A&M. And he just had a textbook that either was just published or is about to hit the presses here. And so I will probably update this. One of the frustrations when we get into some of these BNA and empirical Bayes studies is that there are several different sets of nomenclature where you have like alternate symbols and nomenclature for the same things as we compare the Highway Safety Manual to some of the foundational research you'd find in the peer-reviewed research literature. And so I'm in the process of trying to bring those in line with one another, but I don't have a great solution to that yet. So I'll apologize in advance because I'll introduce a bunch of content today, and then when we get into the HSM, um, as a I think it's largely as opposed to just using a bunch of Greek symbols, which may read as jargon to practitioners. The HSM terminology is focused. It's more practically oriented, and as a consequence, the naming convention kind of follows that. But we'll talk about that a little bit more as we get into next week. But from a big picture perspective, we talked about this previously in setting up some of the evaluation framework. So the simplest study would be a naive before and after. And so in that circumstance, we've got some site or sites where a treatment has been applied, and in lieu of any other information, our best guess as to how many crashes we would have seen after that treatment had been applied, but in the absence of the treatment. So if we hadn't done anything, our best estimate would be whatever number of crashes we had experienced prior during that preceding period. Okay. And if the treatment is in fact implemented, then our evaluation of how effective it would be, or by how many crashes were reduced, we'll indicate that quantity as delta here, and that's just simply the difference between the number of crashes before and after. Okay. And so, again, apologies, there's a lot of nomenclature here to familiarize yourself with, but generally the parameters are being denoted as Greek letters here, and then the statistics that are estimating those parameters would be our normal Roman alphabet. And so consequently, in this case, we're interested in this quantity kappa minus lambda or k minus L as the case may be here. And we'll also refer to those quantities generally as pi and lambda. And so when we talk about lambda, that's basically the number of crashes that we're expecting in the after period. For all practical purposes, that's the number of crashes that we would actually observe after that treatment's been implemented. Because if we look at the after period data, we don't have the same concerns with the regression to mean as we would in the before period, because generally speaking, we're assuming that after period data is generally random and representative. And so there wouldn't be a need to directly account for any regression to the mean effect in that circumstance. Okay, so it would only be trying to adjust this before period crash data due to the fact that we expect this as high as it would be compared to a quote unquote normal year. Now, we're just starting with this simple naive before and after here, but I'm just saying this in part for setup here. Okay, and so in addition to that, we're also interested in pi, and pi is generally the number of crashes we would have expected to see in the after period if in fact no treatment had been applied. And so in this circumstance, so a number of crashes during the before period K is basically an estimate of each of those respective parameters, okay? And so from our perspective, we're primarily interested in two different things. And in the broader literature, we would refer to this delta as just the change in crashes, or generally speaking, they should be the decrease in crashes that we would experience. Now, in some circumstances, of course, you may have a treatment that just doesn't work for whatever reason, and so we could end up with negative values for this. But generally speaking, this is parameterized such that it's going to give us the number of crashes that were reduced between the before and after period. And then we also have a measure which is referred to as the index of effectiveness. And so this is just basically the ratio of the number of crashes we experience after the treatment had been implemented to the number of crashes we would have expected to see without the treatment having been implemented. There's a very minor adjustment factor here that I'll get to in a second. But if we just look at that ratio, I think they should be somewhat familiar. I'm trying to remember what we've covered in this class and what you would have seen previously. But if we take that ratio of the crashes that occurred after over the crashes that occurred before, is that familiar to you guys in any context? Have you heard of the term crash modification factor before? Okay, so that's basically a CMF. So for example, had we implemented the treatment, and let's just use nice simple numbers, and our crashes were reduced from 10 to 9, that ratio then would just be equal to 0.9. And so the CMF for implementing that treatment would be 0.9. The corresponding crash reduction factor would be 10%. And so again, apologies because I'm just basically going from the research literature here. And so that prior to the introduction of the HSM, the early literature just referred to that as an index of effectiveness, but those are basically synonymous or analogous terms, okay? And then this last point down here, this is basically just a minor adjustment. So a lot of the statistical tests that we've worked with in 849 and we'll also work with in this class, we're generally using some properties of the normal distribution in some cases, but as you'll recall from preceding discussions, crashes are generally distributed as Poisson. And so this is just a very minor adjustment. And so what this is doing in practice, it's going to basically dampen that CMF or make that CMF slightly smaller, and that is reflective, at least somewhat, of partly of the uncertainty that's inherent in the crash generation process. And then it's also somewhat of an adjustment because we would tend to slightly overestimate that CMF if we just relied on the raw counts. And so we've established previously that one aspect of the Poisson distribution is that the mean and variance are equal to one another. And so in short form, this adjustment is just 1 plus 1 over pi, where pi is the number of crashes we'd expect to see in the after period. And so just from looking at this then, as we have data for either a large number of sites or as we tend to experience higher numbers of crashes at individual sites, This pi term gets very large, and then this term just converges towards 1, and that's eventually just converging towards a simply calculated CMF. Does that make sense? Okay. All right, so, and this is just kind of restating what was on the preceding slide. So in practice, these are all parameters, and so we don't know what these numbers actually are, but we're representing them using sample data. And so with that being said, we're interested both in what the mean or expected value of these parameters are, as well as the variance of these parameters. And that relates back to just hypothesis test procedures. And for example, if we want to determine whether that reduction in crashes is statistically significant at some prescribed level of confidence, for example, okay? And so when working through this, it's basically a 4-step process. And my apologies, because I know my animations are a little bit screwed up. I was trying to fix those before class here today. But the first step in the process is to estimate how many crashes we'd expect to see during that after period, the post-implementation period, if the treatment had been applied versus it not having been applied. And so in our case, that's real simple. We're just collecting crash data for those before and after periods. And then in addition to estimating those mean numbers of crashes or the expected numbers of crashes, we're also interested in the variances. And as it turns out, we can use the properties of the Poisson distribution. And so that's also quite easy in concept because the variance is simply equal to the mean in the case of that distribution. And then we take that information collectively to estimate those two parameters that were introduced previously. So the change in frequency or the reduction in crashes, and then likewise that crash modification factor that's due to the implementation of the treatment, basically, okay? And so simply speaking, delta, as was illustrated on the preceding slide, is just pi, which you'll recall is the number of crashes we'd expect to see if the treatment hadn't been applied, versus minus lambda, which is just the number of crashes that were actually experienced after the treatment, okay? And then likewise, our index of effectiveness, the crash modification factor, is just the ratio of lambda over pi with that small adjustment on the denominator, okay? And then the variance of those, and we covered this I think in passing, or I don't know if I had a lot of coverage in this in 849. But when we take random variables, and if we're either adding or subtracting those random variables, then their variances are additive. So if we were looking at the quantity pi plus lambda or pi minus lambda, in either of those cases, the variance of that sum or difference would just be the sum of the respective variances, okay? And then it's a little bit more complicated when we're taking the variances of ratios here. But in short, we're basically taking that index of effectiveness and squaring it. And then we have some adjustment factors here. And it's similar in nature to when we had worked through some of the other parametric tests in 849, where this is largely accommodating A, the variability, and then B, the sample sizes that we're working with. And so, based on step 2 up here, this term is just going to reduce to 1 over lambda. This term is just going to reduce to 1 over pi. And then similarly down here, this will be 1 plus 1 over pi, and that quantity squared, okay? And so basically, when we're taking variances of ratios, we have this multiplier effect instead of the additive effect is the short version of that. There's a much longer tangent that I'd prefer not to go into right now, but that's just basically the general setup here. If we're taking differences, we add the variances. If we're taking ratios, we square those differences, those variances, okay? All right. Now, when we work through these in practice, it's advantageous to us. The way the math works out essentially is if we take that number of crashes that's experienced after the treatment's been applied or the expected number of crashes based on the before period data, we can simply add those across our individual sites. And so the big advantage there, if we think back to the preceding terms, is that as we increase the number of crashes, then it becomes more straightforward, and we're converging towards just that simple ratio of lambda over pi for the crash modification factor as an example. And it turns out the variances in this case are also additive across sites. And so we would calculate the variance for each individual site at which the treatment was applied, and then we'd sum that across all sites. Or if we're looking at multiple years, we'd sum it across all years within the sites and then across all site years over the entire sample. Okay.
So, Dr. S, does that mean that the variance of lambda hat is also equal to just the sum of lambdas if variance of lambda I is just lambda I?
Right. Yeah.
Okay.
So the math, it works out.
I guess I'm
The
saying does it still cancel out to just like 1 over lambda and 1 over pi in the preceding slide equations for like variance of theta?
Yes.
Okay.
So that's these terms are basically used interchangeably in the preceding analysis. Okay.
Okay.
All right. Any other questions on this? Just feel free to interrupt me as we work through it. This is we're starting with the easy stuff. Now, this slide was supposed to be very nicely animated. My apologies. It's not. But so we've just got an example here. So let's assume we've got a sobriety checkpoint program that's aimed at reducing alcohol involved crashes. And so in a given district, maybe we had 150 crashes of that type prior to the implementation of this program. And then afterwards, that was reduced to 125. And so based on that, we essentially want to determine whether or not that reduction was statistically significant. And so in our setting here, our estimate of how many crashes we would have seen afterwards if the program hadn't been implemented is just that same 150 here, right? So that's our estimate pi. The number we actually experienced after it was implemented was 125. And so our crash reduction here is 25 crashes as a consequence, okay? And as established previously, the variances of those respective quantities are 125, 150, and then 275. So again, mean and variance are just equal to one another for the first two terms, and then we're adding those respective variances here. I'm subsequently taking the square root of that, which gives us a standard deviation. And again, roughly speaking, the distribution is relatively similar to a standard normal. And so if we go plus or minus 2 standard deviations, we can use that to construct a 95% confidence interval around this difference you see right here. Okay. And so in our case, then, twice that quantity would give us roughly 33. And so that 95% confidence interval is going to go from roughly -8 all the way through, what do we got, 62 or 63, whatever the case may be there. The net takeaway there is that that confidence interval does include 0, so we wouldn't be able to conclude that this was a statistically significant reduction, for example. A short way of doing this is we could have just gone also to those Poisson charts that were introduced a few weeks ago here. And so this is basically the way we would work through that on a case-by-case basis, okay? Secondly, the index of effectiveness here. So again, we're just taking lambda over pi, and then we have that very small adjustment factor. And so we've seen roughly a 17.2% reduction in crashes. So I'm just taking 1 minus that quantity. And then the variance is calculated as shown over here. We take the square root there. And so that standard deviation of that estimate is equal to 0.1. And so if we double that and construct a confidence interval around theta here, then that is basically ranging from roughly 0.63 up to 1.03 nearly. And so since that interval includes 1, just as we saw in this case, while we've seen a reduction, that reduction is not statistically significant at 95% confidence. Does that make sense? Okay. So relatively straightforward. As we move into the before and after with control, we're going to use a very similar approach, except we're going to start to introduce some adjustments here. again, operating under the assumption that there are other external factors that are also at play here. And so we want to control for them by including an appropriate comparison group. Okay. And so we've gone through this setup before, so I'm just including this here for reference basically, but the next slide should have general details. And so the one big difference here between the before and after periods, our setup is quite similar here. So we're again interested in our differences in the before and after crash counts, but we're also interested in those before and after crash counts at the control locations. Okay. And so in terms of setup here, we'd be interested in taking the ratio of the crashes between the before and after periods in both the comparison group and the treatment group. And so we're using this comparison group as essentially an analog. We would expect to see the same general trend occur at the treatment sites if no treatment had been applied, right? And so we take the after period crashes over the before period crashes here, and that would be analogous to basically taking the ratio of the after period crashes to the before period crashes at the sites where the treatment was applied. And so our operating assumption here, like I said, is basically that those proportions are roughly equivalent to one another. And so we're just operating under the assumption that whatever difference we see in the control site, that same effect is going to hold at the treatment sites. Okay. And so our primary quantities of interest are going to be calculated in the same way. And so really the only substantive difference here is that we're taking that before period crash count and we're just multiplying it by whatever that corresponding ratio is. Okay. And so just kind of looking at that schematically there. So in this case, in a simple before and after design, we'd just be taking the difference. If we were to project this straight over, we'd be taking this difference as a measure of the effectiveness. Now, in this case, and this could be due to increases in traffic volume or any number of other things, we see that crashes are generally increasing between those before and after periods. And so all we're doing here is we're taking this initial estimate and we're scaling it up by whatever the slope of this line is, basically. Make sense? And so consequently, then delta in this case is simply the difference between these two quantities. And we can calculate theta as a ratio as we had previously as well by taking lambda over pi. Okay? All right, and so just working through the steps here, everything is very similar to what we'd seen previously, with the caveat here is that we're introducing this adjustment factor R, which is just accounting for that general change in crashes that's occurred between the before and after period. And so we adjust our before period count by that ratio. We're assuming that same ratio applies for both the treatment and control groups. The variances for lambda, again, it's just going to be whatever the variance and the mean are equal to that same quantity L. Pi is a little bit more involved here because now we also have some other sources of variability that we need to account for here. And so instead of the variance just being equal to the mean in this case, you'll notice there's a bit more of an involved calculation here. Now this estimate K is generally going to be close to pi. And so let's just ignore this term for the time being. If that term were 0, we'd be just back where we started with that variance and mean being equal to one another. Okay, everybody with me there? And so then this is just a minor adjustment, which is largely going to be dictated by those respective sample sizes. And so as our samples get really large, and this is going to be a recurring theme, this term will tend towards 0 and will tend back towards this general relationship where the mean and variance are equal to one another. Okay. And so the second term here, this intermediate term, is just, it's roughly equivalent to 1 over m plus 1 over n, where those again are the corresponding numbers of crashes that were experienced at those control locations. Okay. Pardon me. And then this term, since we're assuming that this ratio is roughly equal to 1, this goes to 0. Okay. So in other applications, it would be possible to try to estimate these quantities directly, but just based on the research literature, that generally makes a very small contribution. And so then this simplifies down to just 1 over K plus 1 over M plus 1 over N. Okay. All right, and then estimation of the measures of effectiveness is straightforward and very similar to what we'd seen previously. So we're just taking the difference between the expected crashes after treatment and what was actually experienced. We calculate the index of effectiveness, or the CMF, in a similar manner, and then the variances of those respective quantities are calculated in an analogous manner. So that the setup's nearly identical. The only difference is just we're using that scaling factor, that R, to account for the contemporaneous changes that occur between the control group and the treatment group. Does that make sense? Okay. It's a lot easier teaching courses to 2 students when you can actually see responses. So time permitting, I want to go on a tangent on that at the end of today's lecture, but let's see how time looks. Okay, so we're going to basically just revisit the same problem we had looked at previously. So we've got the sobriety checkpoint. We've given that crashes were reduced from 150 to 125, but we're given, for whatever reason, and there's could be different reasons for this occurring. Maybe more stringent laws were reduced, or there were other policies or programs that were introduced more broadly. And so we tended to see a decline in alcohol-involved crashes in other districts as well. And so as a consequence of that, we would suspect that the reduction in crashes we saw under the naive before and after design may have been overstated as a consequence. Okay. And so we're just going to basically work through an example here where we account for the fact that we did see similar reductions, though not of the same magnitude, at other locations where that program had not been implemented. Okay. And so as we had done before, we're starting with our crash counts for the before and after period for both the treatment and control group. And so we've seen basically a decline of 6.25% in the control group from 160 to 150. And so we would expect to see that same reduction in the 150 crashes we saw in the before period, even if we didn't do anything. Okay, so if the program hadn't been implemented, instead of experiencing 150 crashes, we would have expected to see around 140. Okay, and so consequently then, we're evaluating a reduction from that 140.625 to the 125 that we had actually experienced. Okay. As noted previously, we're assuming this same ratio applies for both the treatment and control groups. Our variances, just working through the calculations that were presented previously for the observed after period crashes, that variance of 125 is equal to the mean. And for the expected number of crashes, it's that 140.625 plus 1 over K, which in our case again was 150, plus 1 over M plus 1 over N. Okay. And so in total, then that gives us an estimate of 389 roughly for that variance. And so on the next slide, just working through the calculation. So our reduction in crashes in this case is 15.625. So that's obviously less pronounced than we saw in the before period. The variance of that quantity is 514. And so taking the square root gives us 22.67. And so if we constructed a 95% confidence interval, that's obviously going to be much wider. And so that's going to include 0. And so since we didn't find a significant effect in the preceding analysis, we're obviously not going to find a significant effect in this analysis because the previous analysis had overstated the magnitude of that effect. Okay. Likewise, when we calculate our index of effectiveness, we see that now, instead of being 0.82 or whatever it was in the preceding, it's now at 0.87 with a variance of 0.02, standard deviation of 0.14. And so obviously, if we double that standard deviation, that's going to significantly exceed 1. So we're not able to find a significant reduction in that case either. Okay. All right, so it'll get a little bit more complicated as we get to the next slide, but let's just check, are we all on the same page here? Does this make sense so far? Okay, awesome. Okay, so the empirical Bayes method. So if we think about the way this is structured, we previously were looking at K as an estimate of kappa, which in turn is used to estimate pi, or the number of crashes we'd expect to see if the treatment hadn't been applied. And so in the before and after with control, we provide an adjustment that allows us to control for general changes that occur external to whatever treatment we had applied, but we don't explicitly address the regression of the mean concern in the before and after with control. And so that's where the empirical Bayes becomes useful, because in addition to controlling for those other factors that affect crashes, we want to somehow adjust for the fact that we may have observed crashes at a high point. And so consequently, and this builds upon the content that was introduced in last week's recorded lecture. What we're basically doing is we're determining that expected value for the number of crashes during the before period based on two sources of information. So first of all, the number of crashes that are actually experienced during that before period. And then secondly, the number of crashes we would expect to see during that period using a safety performance function or a regression equation that had been developed based upon a number of similar sites. And we're weighting those two factors accordingly by this weighting factor W here. And so W is basically going to be equal to 1/1 plus, here I'm referring to it as alpha. This might cause even more confusion and frustration. You'll also see that referred to in some cases as K, which I've avoided here because we already have a K and a kappa. But when you estimate regression models, we typically estimate them in the form of a negative binomial, and we haven't got into this in 849 yet. So do you guys have some degree of familiarity with a negative binomial? So basically, it's a generalization of the Poisson model. What we tend to see when we look at empirical crash data is that assumption that the mean and variance are equal to one another is somewhat tenuous. What we often find, particularly at locations that have relatively low numbers of crashes, is that the variance can be significantly larger than the mean. And so the negative binomial model basically results in, it looks like a Poisson distribution, except it's got fatter tails and a lower peak. So similar to if we compared the t distribution to the standard normal distribution. And so this alpha term is basically giving us a sense of how much extra variation there is. So for example, if this converged back to 0, it would mean we're just simply back to the Poisson case that we had started with. Okay. And so as that gets larger, it's reflective of additional variability in our data set. Okay. And so that's one factor that comes into play here. The second is simply the expected number of crashes that we see based upon that regression equation. So for example, we'd have this SPF that's been developed for the control sites. We would plug in the pertinent information for the sites where the treatment had been implemented, and that would be the basis for this estimate. Okay, so it's we're basically building off the content last week. We're just looking at the mean number of crashes that occurred within a control group that was similar. In this case, we're introducing a slightly more sophisticated model to arrive at that type of estimate instead. Okay, that makes sense? Okay, and so as we look at this, functionally, it's helpful if we kind of think through when we apply more weight to the site-specific data versus the regression equation, okay? And so if we look at the way this is structured, W is a weight that's being provided, applied directly to that regression equation. And so as you'll notice here, what tends to happen as that over dispersion parameter gets larger, what's happening to our weighting factor? Yeah, so that we're applying less weight as alpha gets larger. Does that make sense in concept, why we would do that? So basically, as our alpha gets larger here, it's telling us that that regression equation, that safety performance function, is significantly more variable. Okay, so if we look at how much variance there is in the predicted values. If alpha is say 0.5 versus 0.05, there's much more variability in the case where that term is larger. And so in a general sense, larger values of alpha simply mean that those equations are less reliable. Okay. And so if the equation is less reliable or less precise, it would make sense that we would give less weight to it and more weight to what we're actually observing at the site. Does that make sense? Okay. And then the second component here relates to the expected number of crashes from that regression equation. And so as the expected number of crashes at the site gets larger, what happens to that weighting factor? Yeah, Travis, you can make the same gesture. Yeah, exactly. So as that expected number of crashes goes up, that weighting factor also goes down. Does that make sense in concept? Okay, so what's happening there basically, and we've talked about this quite a bit, regression to the mean is a particular concern when we have very low numbers of crashes. As we increase the number of sites, or as the number of crashes experienced on a site-by-site basis gets larger, we gain greater confidence in that site-specific crash count. And as a consequence, we really don't need to rely as much on the model in those circumstances. Okay. So hopefully, I think that's critical, and that's a point that's not particularly well explained. Like in the HSM, it doesn't outline any justification for why. It just kind of shows what the equations are. And so I think that's a point that's often lost on particularly the practitioner community. It kind of turns into like a black box. But if you understand that, I think it kind of helps you to think through procedurally how the EB method works in essence. Okay. So we're basically accommodating here the degree of precision from that equation, as well as the degree of precision we believe to have with the site-specific counts, because as this term gets larger, we would gain more confidence in the actual raw count at that site. Okay. All right, and so as we look at the setup here, this is very similar to what we saw in the before and after with control. So we have those same observed crash counts for our control or reference sites, as well as the sites where the treatment has been applied. You'll notice the calculation of pi is slightly different here. So instead of just taking r times the expected value from that regression equation, we're also taking the ratio in time periods. And so this is an important point that we hadn't really talked about previously, but oftentimes we'll run into a circumstance where we may have different durations of data between the before and after period, for example. And so as we walk through this, the expected number of crashes that this estimate pi you see here is going to be a function of that weighted average that was detailed on the preceding slide. And as you recall, in the preceding slide, that was working with just data from the before period, okay? And so we also want to account for the fact that there'll be some inherent changes between the before and after period, just as we had done in the before and after with control. So the first step that we just walked through was how we refined our adjustment for the pre-crash or the pre-treatment period, okay? But then we need to extrapolate that forward so that it's in line with what we would expect to see after the treatment, because there could be other changes, which again, in this case, are being captured by trends that we see from the reference sites or from the equation that is based on those reference sites. And so consequently, this first adjustment here is very similar to the R that had been introduced previously. And so we would take the information for the sites where the treatment was applied, and we would use it to estimate how many crashes we would expect to see in the after period divided by how many crashes we would have expected to see in the before period, okay? And so the only differences there basically in a lot of these safety performance functions would be traffic volume. So at a very simple level, we could have just taken a ratio of the changes in traffic volume if we assumed a proportional relationship. But as we've talked about previously, we tend to see, and I hope I'm doing this in the right direction here, It starts to taper off, and the increase is less rapid at higher volumes due to congestion effects and some other factors. And so this is basically simply a more refined estimate than if we had just adjusted by traffic volume. So we plug the traffic volumes into the SPFs, and then we would take whatever that difference in the ratio is between the after period volume and the before period volume. Does that make sense? It'll be clearer, I think, once we plug some numbers in here, for example. But so that's the first adjustment, and that is essentially accounting for changes in traffic volume. And then the second adjustment is just whether we have different time periods. And so if we have 3 years of before period data, but only 1 year of after period data, we would take that ratio and we'd take 1/3 of the crashes we'd see during the before period if the after period is shorter. Okay. So just a mechanical adjustment there. And then the actual measures of effectiveness in this case are going to be calculated in the exact same manner we had previously. It's just the intermediate steps we use to get to that estimate of pi are going to be slightly different and slightly more complex in this case. Make sense? Okay. All right, and so if we're just looking at that schematically, this is kind of laying out exactly what some of those differences are here. And so we have an individual project site, we have the reference site, and so we use that first step in the procedure to calculate what that weighted average would be based upon those two sources. Okay, so the actual site-specific information and the information based upon that regression equation. And so that gives us a number that's somewhere between those two. It's going to tend towards the project site if we've got a very high value of alpha or a lot of over dispersion in our equation, or if we have a very large number of crashes or a very large number of sites. Okay. In the case where we've got lower crash counts, lower numbers of sites, or more reliable equations, it will tend closer to the cluster of the reference group. Okay. And then adjusting that to the after period, we're basically taking those two sources of information. So the change in expected crashes, which is largely capturing changes in traffic volume, times the change in whatever the duration of the after period is relative to the before period. If we've got 3 years of data, for example, in both cases, obviously that term's just one, it drops out. And then our estimate of effectiveness then in this case, instead of being the difference between this point, if we projected that out, and this point, is now the difference as indicated here graphically. Okay, so I think the diagrams are fairly helpful in trying to think through procedurally how these are working. So hopefully that's helpful. Now, calculation of the variances for those counts is as indicated here. So for our expected number of crashes from the regression equation, we're just simply taking whatever, we plug in our data, we calculate that mean expected number of crashes. And then instead of the mean and variance being equal to one another, as we had talked about previously, this is where that over dispersion term comes in. And so if the over dispersion term is equal to 0, as we had talked about previously, this collapses to a Poisson, and we're back to just our variance and mean being equal to one another. Okay. But in instances where we do have extra variation, we basically will see that this variance becomes inflated depending upon how large that over dispersion value is. Okay. And then likewise, for the expected number of crashes, in this case, we're just pulling in the information about our weighting factor, and we're applying that directly to our estimate. Okay. Okay. And so, sorry, there's a lot of text here. But as we work through the process here, the first step would be to develop a safety performance function, so a regression equation using data from that reference group. And so that's the second set of lecture materials that I'll prepare for either later this week or early next week, and we'll actually estimate one of those SPFs. For our purposes today, I'll just show an example, but so that expected value of kappa, so the number of crashes we'd expect to see based on the control information, is going to take the form of a negative binomial model. Functionally, there's no difference in terms of what the parameters look like between the Poisson and negative binomial models. The big takeaway here is that function is going to take an exponential form. And so we'll talk about that more in subsequent lectures. And when we estimate those safety performance functions, and we'll probably get into using SPSS, but there's a number of other programs we could use as well. An output from estimating that negative binomial model is alpha or K or whatever designation they use for that overdispersion parameter, okay? So we estimate the model, we get coefficients, we get our betas, just like we had talked about in the linear regression framework in 849. And then we also get the overdispersion parameter, which doesn't affect the expected number of crashes, but it's capturing and allows us to estimate the variance for the crashes based upon those site-specific factors, okay? And then calculating our expected number of crashes, this just relates back to what we had shown previously. So I put this in long form here, but this is basically W and 1 minus W. So I don't know if it's more or less clear in long form here or short form, but that's all we're showing right here. And then the variance of that, again, is just in this case, 1 minus W times the expectation we get from this weighted average, okay? All right, and so there's a few notes down here further detailing that this is our actual observed number of crashes. This is the predicted number of crashes, and then this conditional estimate is basically a weighted average of the two, okay? All right, and then that ratio, like I said previously, that's generally accounting for the effects of volume. And so we would take the data for that site during the after period, and we would take the data from that same site for the before period, plug that into the regression equation, and then we would just basically be scaling up or scaling down our expected number of crashes based upon whether or not we saw a general trend of increases or decreases in crashes due to those external factors that would have changed between the before and after periods, okay? And we plug that information in as well as the ratio of those time differences, and that's how we then get to our estimate for pi at the last step. And then from that point, everything is very similar to what we had seen previously, with the one caveat. We would account for this 1 minus W with respect to the weighting factor when we're calculating the variance of pi here, okay? Okay, and then once we've determined pi, everything else is calculated exactly as we had seen in the BNA and BNA with control steps, okay? So much of the same. And so we'll return one last time to that same set of sample data we had used previously. In this case, we still have that one district that's our reduction from 150 to 125 crashes. But let's assume we looked at data not just from one other district, but from a whole bunch of other districts. And we basically found the number of alcohol-involved crashes is expressed given the functional form we see right here, okay? So the exponential of this is basically like beta naught. This is our intercept term here, basically. Our beta is 0.75, and our x is simply the VMT, which in this case is measured in millions. And we're logging that. What that means in practical terms is we could take this VMT outside of the equation, and it would be VMT raised to the 0.75 power times the exponential of 2.28. And so I bring that up because in the functional form of these SPFs, this is generally, we almost always will log either AADT or VMT. And so this is telling us what the elasticity is between crashes and traffic volumes. And it might have been a while since you've had an economics course, but when we talk about elasticity, what that means in loose terms is that a 1% increase in traffic volume would correspond to a 0.75% increase in crashes, okay? And so that gets back, if this parameter were equal to 1, or in some instances we might constrain this to be equal to 1, that would be forcing a proportional relationship. So if you doubled your volume, you double your crashes. In this case, it's starting to taper off as we had indicated previously, and so it's increasing at a decreasing rate, okay? And so in addition to this information, we're told that the VMT in this specific district had decreased from 36.5 million to 36 million between those periods. And so as a consequence of that, just as we had seen in the preceding before and after with control case, we would have expected to see fewer than the 150 crashes due to various factors, which would include regression to the mean, as well as any contemporaneous differences in volumes between those periods. Okay. And so the first thing we do, we apply that safety performance function. We're given from our output that alpha was equal to 0.1. We know that we've experienced 150 crashes during the before period. And so if we compare that estimate to what we would see for similar sites, we'll notice our experience at that site was larger than the typical site. And so 145.18 is what we would expect based on the regression equation. We're calculating our weighting factor here, and so that alpha of 0.1 is multiplied by that expected count from the SPF, and so we're applying a weight factor of only 0.064 in this case, and so generally speaking, that's relatively small, and part of the reason for that, in large part, is that this is a fairly large number of crashes, 145.18. Within, and so if you think about this in concept, we're looking at crashes across an entire district. And so we would expect to see less regression to the mean than if we looked at crashes at just an individual site, right? If you just think about the magnitude of that, you're probably not going to see very heavy regression to the mean district-wide. But as we narrow in and get to a more narrow range of analysis, we tend to see larger weighting factors applied to that regression equation, okay? So in this case, it's almost as if we've done a whole lot of additional work for not a lot of benefit here, because that 150 is basically just reduced down to 149.69 in this instance, okay? Now, as a consequence of that, what also tends to happen here, and this is common with and one of the advantages of the empirical Bayes method, is that we're also able to get a more precise estimate or a lower variance estimate. And so that variance now, instead of being assumed to be equal to 150, that's been reduced to 140.11. Okay, so that would be one of the other advantages, despite the fact we've just had this relatively modest reduction in our expected number of crashes. That R factor, so as I had indicated, all we're doing here is basically trying to scale up, or in this case, scale down due to that traffic volume decrease. And so we plug in our before period volume of 36.5 million, our after period of 36 million VMT, and we basically see a 1% reduction in crashes as a consequence, okay? So we reduce that 149.69 a bit further, and so now instead of being at 150, we're at slightly over 148. And from there, we can then go through, calculate our mean and variance for lambda, calculate our variance for pi, which you'll notice is reduced even a bit further here to 137.26. And so now at the end of the day, our reduction is now, instead of 25, it's 23.2 crashes roughly. Our variance of that estimate is 162.26. And so the standard deviation is 12.74. So we're almost to the point where this is a statistically significant reduction. We're adding, 25.5 there. So it's just a little bit past that. So not quite significant at 95% confidence. Likewise, when we look at theta or at our CMF or index of effectiveness, the standard deviation of that quantity is 0.1, and so that gets up to 1.038. So again, it's just beyond the level that we would find that to be statistically significant. So we're getting closer, but there's not enough evidence here to say with 95% confidence that we've seen a significant reduction. Okay, I think that wraps up what I had for today. Yep. So hopefully that helped to kind of reinforce the differences between these methods. And then the next set of slides I'll pull together will demonstrate how we do this using the nomenclature in the highway safety manual, and then using some real data to estimate those safety performance functions. Okay. And so timing wise, we're good for once here. So we've got about 4 minutes left. I don't know if either of you have questions on anything we've covered up to this point.